In this video, we're going to be looking at rational functions, identifying vertical asymptotes, and defining their domains. So we have a rational function, which I've written down. A rational function is just a quotient of two functions, meaning it's one polynomial divided by another polynomial. And whenever we have a quotient, we need to remember that this denominator cannot equal 0. Because if it equals 0, then we have a situation in which that quotient is undefined. So in this particular case, that means this bottom polynomial, d of x, cannot equal 0. So we have to put some restrictions on this rational function. We would say something like this: d of x cannot equal 0. And then we'd have to find values of x that make d of x equal 0 and exclude those values of x. So let's look at an example. So we have f of x is equal to 2x squared plus 1 divided by x plus 1. Okay, so here is one polynomial in the numerator. Here is one polynomial in the denominator. So if we're going to find vertical asymptotes, we are going to look for the restrictions for this particular function. So the denominator cannot equal 0, which means, in this case, x plus 1 cannot equal 0. So now I'm just going to solve this like an equation. So I have found that x cannot equal -1. X can equal any other value except for -1. So that means that we have a vertical asymptote at x is equal to -1, and that the domain is all real numbers except -1. So let's take a look at a graph just to see how this function looks. So here we have our function, okay, and I can zoom out a little bit. Now, what does it exactly mean that it has a vertical asymptote at x is -1? Well, let's actually graph x is -1, and you'll see, okay? Oops, that is x is 1. Okay, so when x is -1, you could see that this function never crosses x is -1. And that's going up in the positive y direction. The same thing exists in the negative y direction. As I scroll down, okay, it looks like it is crossing it, but as I zoom in, you can see that that's not the case. So that vertical asymptote means the function gets really close to it from the left side, and it gets really close to it from the right side. So though the question doesn't ask this, we could say as x approaches -1 from the left, f of x, that's our y values, get really negative. Okay, and that was the portion of the graph that is going down. And then as x approaches -1 from the right, our y values are going to get really positive. So as x approaches -1 from the right, f of x, our y values, are getting very positive. And this notation right here, this little minus sign, just means from the left. And the little plus sign means from the right. Okay, so though the question didn't really ask for that behavior, just felt it was a good time to bring that up. Okay, what the question did ask was for our vertical asymptote and for our domain. Okay, let's look at a couple other examples. So we have g of x is equal to x squared minus x minus 2 divided by x squared minus 4. So anytime you're dealing with rational functions, it is a good idea to factor both the numerator and the denominator. And even though we only need the denominator to answer this question, I'm going to factor the numerator while I'm here. So we got x minus 2 times x plus 1. You can check your outers and inners to make sure that works. And then the denominator is a difference of two squares, which can be factored as x plus 2 times x minus 2. So, excuse me. So, our denominator cannot equal 0. Our denominator here is x squared minus 4. That cannot equal 0. I've just factored that. So that means at this point I'm going to use the zero product property. X plus 2 cannot equal 0. Or x minus 2 cannot equal 0. And again, I just solved this. So x cannot equal negative 2. Or x cannot equal 2. Okay, so that means my domain is all real numbers except positive or negative 2. And my vertical asymptote, which I often abbreviate as just VA, so if you ever see me write that, my vertical asymptotes, I have two of them. I have one at positive 2, and I have one at negative 2. So let's see this graph just to make sure that that's accurate. Okay, so there's my function. And if, let's see, x squared minus x minus 2. Okay, just checking that I typed that in right. And I found that there's a vertical asymptote at negative 2. And I found that there's a vertical asymptote at 2. Okay, so the one at negative 2 certainly looks like a vertical asymptote. Okay. X equals 2, well, that doesn't look like a vertical asymptote. So why is there a problem here? Well, let's go back and look at the way we factored this. You could see that when I factor this, that I have a factor in the numerator and a factor in the denominator that is the same. So when that occurs, what happens is we actually get a hole in the function. And I'm going to talk about that in the next video. But what you need to know now is if you have a factor in the numerator and the denominator that is the same, that you are not going to have a vertical asymptote at that place. So this right here, which resulted in x is 2, that is not going to result in a vertical asymptote. Okay. So our vertical asymptote is only at x is negative 2. However, that value is still excluded from the domain. Okay, it's still going to be excluded from the domain. Now, our last example, h of x is equal to 2x divided by 3x plus 1. So I cannot factor either the numerator or the denominator. So I'm still going to go to my next step. My denominator cannot equal 0. 3x squared plus 1 cannot equal 0. I'm going to solve this. So I'm going to subtract 1 on both sides. So 3x squared cannot equal negative 1. I'm going to divide both sides by 3. So x squared cannot equal negative 1/3. And then I'm going to take the square root of both sides. So x cannot equal positive or negative square root of negative 1/3. So this, we're taking the square root of a negative number here. This is not a real number. Not a real number, which means that there's no real number exclusions. So that then means that we have no real number exclusions for our domain, so our domain is all real numbers. And I'll put no VAs, no vertical asymptotes. So let's go to Desmos one more time and take a look at this one. Okay, so you can see that function right here. As you scroll to the left and scroll to the right, it doesn't look like there are any vertical asymptotes. I can zoom in here. You can see it's kind of like a squiggle, but I don't have anything that looks like the previous two functions, which I'm going to throw up on the graph again, right? So the other two functions that have vertical asymptotes, they both look a lot different than this purple one on the screen here. Okay, so that's how you go about checking these rational functions on whether or not they have a vertical asymptote and if there are any values you need to exclude from the domain because of those vertical asymptotes.